And we're back. Welcome back from Tuesday. Today we will hopefully finish up with our material completing the support vector machine. A little bit of administrative work first. The third homework, which is on validation and regularized regression, is due the 14th of April 2020, 1 second before midnight, 11:59 and 59 seconds p.m. The homework due date originally was the 13th of April, but that was changed to the 14th because April 10th through 13th is Easter recess. So I pushed that date later 1 day or 24 hours. The reading, it can be found on the Blackboard. It is an e-chapter, is a supplement to the book, and it's on Support Vector Machines, all this material that we're talking about. Okay, so when we last left off, I really felt it was important to correct some errors that I made, and so I'll spend a little bit of time doing that and then finish up the balance of today with the new material. And so we talked about the Lagrangian, and this is the Lagrangian, and it's the primal formulation. It's a function of free parameters W, the weight vector, B, the bias term, and these alphas, these Lagrange variables or Lagrange multipliers. And so alpha corresponds to each one of these alphas. That's alpha 1 up to and including alpha big N. There's an alpha for each one of your in-sample points. And so we minimize this expression, our objective for max margin, and this second term, penalty term, if you will, says get the classifications correct. And so we minimize this Lagrangian, the primal problem with respect to W and B, and then we'll get the solution to that minimization and solve for the new version of this expression when we substitute our results from minimization with respect to W and B. And this second version of the function will be a function of alpha, and that's called the dual formulation. We'll then maximize the dual formulation with respect to the alphas. So when we take this gradient, we get the following expressions for W and B. We set them equal to 0 to find the minimum of Lagrangian with respect to W and B, and we then get the following two solutions. The first is a constraint we'll make use of. The sum n goes from 1 to big N, alpha n yn is equal to 0, and we also have W is equal to the sum, where n goes from 1 to big N, of alpha n yn xn. So we take these results from the primal formulation and we substitute them back into the Lagrangian and get this expression in terms of alpha, i.e. our dual formulation. So here's my primal formulation, which is a Lagrangian, and I will arrive upon this dual formulation, which is a function of a single free variable, namely your alphas. So let's begin. So here we have 1/2 W transpose W. So we're going to substitute this expression for W that we solved for in this W. So we have our first W's, W transpose, so we're going to substitute sum, n goes from 1 to big N, of alpha n y n, it should be an n, y n, x n. Okay. Likewise, we're going to make a substitution of that same expression for the other W, that other part of the W transpose W. And we make the observation that we're multiplying the two together. And because of how multiplication works, you can't really have both expressions, both sums have the same index. This is just a dummy variable. So for the second version of W, we're going to make that substitution, but we're going to change the dummy variable for the summation index. So we're going to say the sum for M goes from 1 to big N. That's our summation. And then we write alpha M, Y M, X M. Okay. So we do that multiplication, and we make the observation that everything under that first summation, it has an index, a subscript of N. So these all look like a constant underneath that second summation. So we can rearrange these terms and bring these inside of that second summation, and then we'll just pair all the alphas together, the y's together, and the x's together. And that gives us the following expression. It gives us 1/2 the sum for n goes from 1 to big N, another sum for m goes from 1 to big N, and then we group together alpha n, alpha m, yn, ym, x n transpose, because remember that first term was transpose, x m. Okay, so this is part of our solution. So then we'll apply these substitutions to the second term in the Lagrangian, the primal form. And when we do this, we're going to make some reductions, as it were, using that second substitution. So this expression consists of 3 terms. The first term, if we look at this multiplication, we multiply alpha n times yn times w transpose xn. So we're going to have a sum. N goes from 1 to big N of alpha n, yn, w transpose xn. Okay, so that's our first term. We have a second term, and this has a leading minus, of course. Let me not forget that minus. Our second term, we distribute this multiplication. We have alpha n, yn, b. Our second term, then, is a minus, the sum. N goes from 1 to big N of alpha n, yn times b. And then lastly, our third term, we have that leading minus, and we have alpha n times minus 1. So that's going to be a plus. So our third term, let me write it over here, is going to be positive, the sum. N goes from 1 to big N of alpha n times 1, which is just alpha n. Okay, so there we have it. Now, we'll take a look at these terms. Well, if we look at the first term, we have minus the sum, n goes from 1 to big N, alpha n, yn, w transpose xn. And we make this observation here that it kind of almost looks like this expression that's equal to 0, but there's a problem. It's not exactly, because we have the alpha n, yn, yeah, but it's also multiplied by w transpose. Well, that's a constant, but we also have that xn, which is captured under the summation because it has the same subscript, the same index n. So we're going to keep this expression intact, and we can't further reduce it after we make the substitution. Let's look at this second term here, minus alpha n, yn, b. Well, this b is a constant underneath the summation, and this is where I had that mistake before. The b is a constant, so we can pull this b out. Let me write it up here, out from under the sum, and we'll see minus b times the sum, n goes from 1 to big N of alpha n, yn. So we're multiplying minus b times this expression. Well, wait a minute. From our solution for the primal problem, when we took the gradient with respect to w and b, we got this solution. This was one of them. So anytime we see that sum, n goes from 1 to big N, alpha n, yn, we can substitute that with 0. So let's substitute this with 0. Well, minus b times 0 is going to be 0. So that second term underneath the summation is going to drop out. So what are we left with? We're left with this first term. We're left with this third term. So we say, okay, well, we have this expression from before. Okay. And then we also have this expression. We look at this first term here, and we see alpha n, yn, xn. Okay. We have this w transpose. Oh, wait a minute. W. Let's substitute in what we have for w. So if I substitute in for w here, that same sum, I notice, oh, wait a minute, I'm underneath that summation where the index is n. Mathematically, I'm going to write that in as the sum for m goes from 1 to big N of alpha m, ym, xm. Okay, so I notice when I multiply these together, this summation, substituting in for W transpose, each one of these variables that have a subscript for the summation index n, they look like constants for this other summation involving summation index m. So I can move these all inside, group them together just like I did before, and that gives me the following result. That gives me minus the sum for n goes from 1 to big N of another sum, m goes from 1 to big N, and then I group together alpha n, alpha m, yn, ym, x n transpose xm. Okay. And then lastly, I had that positive summation for the third term resulting from this substitution and distributing that multiplication into the parenthesized expression. And I say plus sum n goes from 1 to big N of alpha n. Okay, so what do I have here? So I have a leading summation of all the alpha n's. Okay, this is my leading summation of all my alpha n's. And then I say 1/2 of this expression minus 1 of this expression. It's the same expression, only the term up front has a leading 1/2. So 1/2 of something minus 1/2 of something is negative 1/2 of something. So that gives me this second term in my final expression. And the observations I make about this, the free variable here are my alphas. The y's, well, those are constants. Those are either +1 or -1. Those are my class labels given to you in the data set. And these vectors, these are just drawn, each vector, from d-dimensional real valued space, R super D. So these are all constants. The only free variables are the alphas. So this dual formulation, L of alpha, is the dual, as it's called, for my Lagrangian. And I arrive upon this by substituting the results from the primal formulation. And I solve this maximization problem. The primal is a minimization, and the dual is a maximization. Okay, so I'm going to maximize the dual formulation with respect to alpha, and each of these alphas must be greater than or equal to 0 for all of the data points. So alpha 1, alpha 2, up to including alpha big N. Likewise, I'm also going to have a constraint, and I keep that constraint on the minimization, on the maximization problem, the dual formulation. I keep that constraint because it involves alphas, and I'm solving for alphas. And the good news is this is an equality constraint. So it's already in a nice form, very amenable to optimization. And so the so-called KKT conditions, Karush, Kuhn, and Tucker conditions, dictate that these alphas must be greater than or equal to 0. Okay. So this is our dual formulation, and this is our form. We're going to maximize with respect to alpha, subject to two things: our constraint that we carried forward when we solved the primal formulation, and we're also going to ensure that these alphas are greater than or equal to 0, at least 0. So they're non-negative. And so we're going to feed this into a quadratic programming problem. And remember, this is a maximization problem. Now, QP solvers, they implement minimization problems. So we need to convert this maximization to a minimization. And how we do that is by negating. If we negate this expression and solve the minimization, well, negating this expression, we now have 1/2 for this term minus that term involving the sum of the alphas. So now our support vector formulation from the dual becomes the minimization, finding the alpha, that minimizes 1/2, a double sum, yn, ym, alpha n, alpha m, xn transpose xm, minus the sum of all of the alpha n's. Okay. Now, one other observation, this expression, that part of the expression, that's an inner product, and we'll talk about that later. But that's important to remember because we're going to take advantage of that in the next module when we talk about nonlinear transformations and talk about kernels. But this we can feed into a quadratic programming solver. Well, it's quadratic in the free variable. That's a quadratic. That's like saying alpha squared. And we have some coefficients, and we're trying to find the alpha free variable that minimize this expression. And so we do this conversion because we want to use a quadratic programming solver. Okay? All right. So let's continue on. So this quadratic programming solver, we can put this expression in vector matrix form. And when we do that, we have our alphas in a vector. So alpha is equal to a row vector. Let's see. Yes, alpha is equal to a column vector. And so alpha is going to consist of alpha 1 up through and including alpha big N. There's an alpha for each data point. And so if we look at this, all right, well, if we have alpha as a column vector and we take alpha transpose, well, that's a row vector. We take this, multiply across and down. We have alpha 1, y1, y1, x1, x1, alpha 2 times y2, and so forth. So we essentially, if we take this product, let me make sure I have everything, x1, x2, x3, yes, that's correct. So if we take this alpha transpose is equal to this row vector, and we compute this expression, well, that's my first alpha, right? That's my alpha n. And then this alpha, that's my alpha m, right? So this first vector provides my alpha n's, and this provides my alpha m's. So I do this multiplication, alpha transpose times a coefficient matrix. These are my so-called quadratic coefficients. Now remember, these are all constants. We had the y's from our class labels associated with our in-sample points, and then we have the feature vectors. These are all constants. So this gives me a coefficient matrix for my quadratic programming problem. We construct this, and we can read it off directly from the data set. Okay, so this first alpha transpose, provides my alpha n from that double summation. This second alpha provides my alpha m from that double summation. And then I have minus the sum of 1 vectors. So this is just my minus the sum of all the alpha I. This is just 1 minus 1 transpose. Right? So we have minus 1, minus 1. We have that minus 1. And the rank of this is big N. And then we have our alphas. We have alpha 1, alpha 2, alpha big N. Okay? So if we do that, that's the sum, and we end up with minus the sum. N goes from 1 to big N of all the alpha n's. Okay? So we have our leading 1/2, alpha, our quadratic coefficient matrix, alpha, the alpha m's, and then we have our second term there from the original QP problem. So our constraint then, subject to y transpose alpha is equal to 0. Now remember, we said alpha n yn is equal to 0, right? That implements our sum. N goes from 1 to big N of, it was alpha n, of all my alpha n's. Okay. So this term here gives us our constraints, and this set of constraints said the sum of all the alpha n's yn are equal to 0. Right? That's what our constraint was. So if we take a look at this constraint here, well, if our y is a vector of our class labels, so y transpose is equal to, it's going to be a row vector, y1 up to and including y big N, and then our alpha is going to be a row vector consisting of alpha 1 up to alpha big N. Right? So we multiply. It's y1 alpha 1, y2 alpha 2. That's the same as saying yn alpha n. Okay. So equals to 0. So this is our constraint. We had that equality constraint, and that's very straightforward. And then we have the bounds on our alphas. We said alpha is greater than equal to 0. That means we have a lower bound of 0 on our alpha, but we have no upper bound. We could say upper bound is infinity. All right, so this is our quadratic programming problem, and we can input this into a standard QP solver, and we have one in MATLAB, and you have an opportunity to use it in an assignment. So in vector matrix form, our quadratic programming solution is a solution to the following problem. 1/2 alpha transpose Q, which is our QP coefficient matrix that we build from the data set. This provides our alpha n's, and this alpha vector provides our alpha m's. So that's 1/2 alpha transpose Q alpha minus 1 transpose, where the rank of this one vector is rank big N, times alpha. Subject to the following constraint, y transpose alpha equals 0, and all the alphas are at least 0. Okay, and so there is quad prog in MATLAB that does QP solving, and I'll direct you to the documentation for that. Okay, so what happens when you run quadratic programming? Well, it outputs a solution. So what happens when you run quadratic programming? Well, it outputs a solution. It outputs a set of values for all of your alphas, alpha 1 through alpha n. Now, of course, we can take this equation that we had from before, from the primal problem, solution to the primal problem. We have a definition now for the weight vector W. It's just the weighted sum, alpha n, xn, yn times xn. So once we have these alphas, we can now construct what that W is. Okay, so the KKT conditions, when we looked at this constraint that said get the classifications correct, we called this term the slack. And we said that for the on-margin points, the slack is 0. So if we have a hyperplane in the dotted line, and here's the top of the margin, is the bottom of the margin, and we said xn is the on-margin point. Now, this is a point such that the slack is going to be precisely 0. And we said the off-margin points, xn, xi, we'll call it xi, the off-margin point, it has a slack. Its distance, the score for this point, is going to be bigger than 1, and therefore the slack is going to be bigger than 1. The slack for this one is 0, because it's right on the margin, 0 slack, and therefore the slack for an off-margin point that is further away than the closest point, the margin point, that's going to have a slack that's greater than 0. So let's take a look at this expression. So the only way for this constraint to be satisfied precisely equal to 0, since we're multiplying two terms, the Lagrange variable times the slack, well, for the on-margin point, we know the slack is 0, okay? For the off-margin point, we know the slack is non-zero, it's greater than 1. The only way for this expression to be equal to 0 is if that Lagrange multiplier, that alpha, is equal to 0. So what does this mean? For the on-margin points, alpha is going to be greater than 0. So for the on-margin, alpha n is greater than 0. And for the off-margin point, the one with a slack that's non-zero, alpha is going to be equal to 0. Okay. And so what does this mean? It means that points that are not on the margin don't really have any bearing in the definition of our weight vector W. That's very interesting. So this KKT condition means that alpha n being bigger than 0 corresponds to a vector xn that supports the margin. It's on the margin. So for the margin points, you can think of them as supporting or holding up the margin. So xn holding up the margin in that point. Another on-margin point is holding up the margin here. And so these so-called support vectors get their name because they're supporting the margin. They're holding it up. And things that are slack, that are more slack, or that have a positive slack, well, they're not holding up the margin. They're not constraining the margin. Now, we've kind of seen something like this before when we talked about regularized regression. If the constraint is vacuous, meaning that, let's say the constraint is this dotted blue line, and it includes the WLN solution, the optimal solution for the unconstrained version, well, what is our regularization parameter lambda? It's 0, because the penalty, this constraint here, the red, does not come into play. Well, there's no constraint if we have a slack that's greater than 0. Because this point is not holding up the margin, it has no bearing on the definition of what the margin is. It doesn't govern the hyperplane. And so this is if we have a non-zero slack, that's like having a constraint like this red curve. Now it's going to have some influence. If we have a zero slack, but if we have a zero slack, an on-margin point, well, that's like this constraint here, this red curve. And that constraint is going to have some bearing on where the definition of the solution is. It sort of pulls and guides the solution. It constrains the problem. And so therefore, we notice that for those margin points with the zero slack, they contribute to what W is. And in fact, W's value is constrained by those margin points. The margin points have a zero slack, and therefore their alphas are greater than 0. Okay, so either the slack is 0 or the Lagrange multiplier is 0. And a positive slack corresponds to a so-called interior point, those points that are in the interior regions of feature space and not on the margin for the hyperplane in feature space. So positive slack means you have an interior point, and for these, the multiplier is 0 because they have no bearing on constraining the solution. And it's like having a regularization parameter lambda being equal to 0. Okay. So these in-sample points that have alpha greater than 0, these are on the margin, and these are closest to the plane, and they achieve the margin, and because they're on the margin, they satisfy this score being exactly equal to 1, which we had talked about when we talked about the development of the measurement for the distance to the margin. Now, if you have this score, we can now redefine for these margin points for which the alphas are greater than 0, or I should say the alphas are non-zero, we can redefine what W is. Instead of summing over all n of the data points multiplying by alpha, we only look at the xn's that are support vectors. And this has the effect of reducing the complexity of W. If W is, say, 1,000,000 dimensions, you don't pay for that 1,000,000 dimensions in the traditional sense. You only pay for it through the number of support vectors you have. Because in the QP solving problem, it was those non-zero alphas, those positive alphas, that were the points that we need to make a decision about. Okay? And so W, its complexity, you have full descriptiveness for the dimensionality of W. But in terms of the cost you pay, in terms of complexity, it's only in terms of the number of support vectors. And the good news is you have a relatively small number of support vectors, even if W might have a rank that's a very high dimension. So you have a high dimensional model, but the cost you pay is in the number of support vectors, i.e. the number of alphas that are greater than 0. And this makes for much lower complexity when you're trying to solve for the model. In this example here, we have 1, 2, 3 margin points, and we have these red, those are interior points. Let me mark them. So these are your interior points. Likewise here, the blue, we have interior points, and these are the margin points. So this one, and this one are all on the margin. So W is defined in terms of the support vectors and not all of the data points, and this gives us a big savings on the complexity, but we have the full expressiveness of the dimensionality of W. And then we solve for W in this fashion, just in terms of support vectors, and then we take any support vector and we solve this equation, and we can solve for what the bias term B is. Okay, and that is our solution. Now, we can take this expression in the dual formulation. Now, we can take this expression for the dual formulation, and this was the dual, and we're maximizing this expression, and of course, to use a QP solver, we negated to solve the minimization problem. Now, of course, for this problem, we input that into a QP solver, and we make the observation in certain parts of this expression. So this is the dual formulation again, and we noticed, and I said before, I alluded to, this is an inner product. Inner product. It's the inner product between each of the vector pairs xi and xj, where I and j are all the data points, I and j are all the data points from your set of in-sample points, right? Even inner product with itself. That shouldn't be transpose. That should be xi transpose xj. Okay. So it's the inner product between all pairs of data points, including with oneself. And here we have the original data set on the left. And this is a non-linearly separable problem. And it's not even a mildly non-linearly separable. This is something that would warrant using a transformation of phi function to get you from your x input space representation to feature space z. Now, we said before early in the semester that you can use a polar transform. You take the x component, the horizontal feature square, you take the vertical feature square, and it measures effectively the distance from each point, rearranges the geometry based on the distance of each point to the origin. Okay, and so here we compute this transformation, and we can still compute the support vector machine by just replacing this inner product in x space with the inner product in z space. And we essentially get, almost for free, the ability to draw highly nonlinear decision boundaries in z space with the cost of just the number of support vectors. It's very, very big savings. And so in doing so, we know that the complexity is a function of the number of data points. In the worst case, if all the alphas, by some weird circumstance, if all the alphas were non-zero, well, we would have n many data points, but your transformation phi could be transforming from, say, 2 dimensions to 1 million dimensions, but we'd pay at most the cost in terms of complexity of n, because we have n of these alphas, one for each one of the n many in-sample data points. And so how you get the solution for this is you replace this inner product with an inner product in feature space, and then you solve this quadratic programming problem for the linear hyperplane in feature space. And then once you get those support vectors in that solution, you map back using phi inverse. So phi gets you this way. You get your support vectors, x, and then you apply the inverse mapping, phi inverse, to give you back what they would be in x space for your solution. Okay, so if we do that, it's important to remember that your support vectors live in feature space. They live in z space. Now, if you took your linear hyperplane in z space and map it back into x space, it would look like this boundary. And you can, in fact, sample from that hyperplane by looking at different solutions to W transpose xn plus b is equal to 1. And you can change your xn and actually do the inverse phi and draw what your hyperplane would look like in the original x input space. But the support vectors live in z space. When you take these support vectors and you locate them back in the original x space, you call them pre-images of the support vectors, because you're taking your support vectors and calling this phi inverse to find what it would look like in the original input space representation. And when you do this, I cast your attention to this mapped pre-image of the hyperplane from z space back to the original x space. This is your original x space. And one thing you'll have a margin that turns with the hyperplane. Let's see if I can draw that. There we go. So there's one side of the margin, and here's the other side of the margin. There we go. All right. You can't really draw very straight, but you get the point. All right. So this is a pre-image of the support vectors, and it's obtained by taking the support vector in z-space and applying the inverse phi function mapping. Okay. And each one of these sustains the margin. You can see this margin here is sustained even when you map back and get the pre-images of the support vectors. It still holds up or sustains your margin, albeit a wiggly margin instead of a linear margin. The linear margin is what you get in feature space, in z-space. And so the result of the generalization, E out, is bounded from above by the number of support vectors. And you use an expectation, because certainly you sample and run this again and again and again, and look at the expected number of support vectors. And so in essence, this is like saying it's dependent on the expectation of the error with respect to support vectors divided by n minus 1. So that's like saying the proportion, the expected number of support vectors that you get as an average relative to the number of in-sample points. Okay, and that's like saying the expected probability of the number of support vectors. Your E out is bounded from above by that. And so here, in this example, you have 1, 2, 3, 4 pre-images of the support vectors. So this means you only have 4 parameters or 4 support vectors in the z-space. And in spite of having a z-space mapping that's in a million dimensions, it doesn't matter how highly dimensional your nonlinear hypothesis is. You only pay a small complexity cost. And it's really important to note that the margin is in z-space. And here we're just representing the pre-image, the inverse phi function mapping to get what it looks like in our original input representation in our X space. Okay. So with that, we'll end there, and we'll pick back up next time on Tuesday with kernels, and we'll look more at how we can do interesting things with this inner product to get even more power out of the support vector formulation. Okay, so again, we have homework due on Tuesday, April 14th, 1 second before midnight. Please make sure you're getting along with reading, and I will see you all